Greetings and welcome to Lecture 2 of Kinematics and Dynamics of Machines. Today we're going to be covering the end portions of Chapter 1 in the book by Wilson and Sadler, Kinematics and Dynamics of Machinery. Specifically, we'll be covering sections 1.8, 9, 10, 11, and 14. And I would, as always, recommend to you that you at least take the time to go through the book, read anything that is puzzling to you in the lectures, and if there are things that you don't understand, please make time to see me during office hours. Let's go ahead and get to it. So, in the first lecture we covered a number of different concepts, and just to review them quickly, these included the degree of freedom. Remember that for most of the mechanisms we will be looking at, we are looking at things that have 1 degree of freedom. What that means in a practical setting is that we need to know at least one parameter of whatever it is we're looking for in order to determine the others. So, to make that explicit, for a 1 degree of freedom mechanism, if we know the position of one link, we will be able to calculate or determine the positions of all of the other links. If we know the position and then the velocity of one link, we will be able to calculate the velocities of all of the other links. Many of the mechanisms that we will be looking at that are of practical use in engineering practice will be Grashof mechanisms. What a Grashof mechanism is a mechanism where one link is capable of revolving 360 degrees, so it can go completely around. These can be defined and determined by this very simple equation. The length of the maximum link plus the length of the minimum link are less than or equal to the sum of the other 2 link lengths. Because mechanical engineering has been around for a long time and because these mechanisms are so commonly used, there are special names that apply to a variety of these mechanism types. One of the most common is a crank rocker. This is where the crank can revolve 360 degrees. The rocker rocks back and forth. It also has a link called the coupler that couples the crank to the rocker. There are several other mechanism types listed here. Again, it's worthwhile taking a quick look through these, maybe trying to sketch them out. So let's talk a little bit about limiting positions. We're going to look at a new mechanism type, one that we hadn't spent a whole lot of time looking at in the first lecture, called a slider crank. A slider crank, again, should be a very, very familiar mechanism type. This is the basic mechanism used for internal combustion engines. It's also quite often used for pumps or compressors. It can be used for a variety of other things, such as stamping presses. What it consists of is a sliding component. We often call this a piston as well as a slider. Excuse me. A connecting rod or con rod, which attaches to what's called the wrist pin on the piston, and the end of a crank. This crank can revolve 360 degrees about center point. If we take a look at the degrees of freedom of this planar linkage, we'll find that it is a 1 degree of freedom mechanism. A couple of interesting things about this mechanism. Again, it's a fairly old mechanism. When we look at this, we see that the piston, that is, the slider, has 0 velocity at what's called top dead center and bottom dead center. These are the positions where the piston is either, for top dead center, as far away from the center of rotation as it can get, or for bottom dead center, as close to center rotation as it can get. And it's be easy to see, if you apply your imagination to this, that at those points, the piston has 0 velocity, but it's about to start moving very quickly, so that's where it has the maximum acceleration. You can also fairly easily convince yourself that when the piston is at top dead center or bottom dead center, any force being applied to the face of the piston is unable to move the piston. The links are lined up, and you can't put any kind of torque around the crankshaft. So putting as much force as you want onto the end of the piston does nothing for you. This has an interesting effect, or something to think about. When we look at single-cylinder engines, we often look at it from the standpoint of a force being generated at the end of the piston due to the explosion of a mixture of fuel and air. That explosion, though, if the piston is truly, excuse me, having a little cough, is truly at top dead center, can't really put anything into the mechanism. It won't be able to move. Hence, we often have a flywheel to maintain motion, so that as the piston carries around, we actually get movement. These kinds of engines have very high inertial forces, and so if you have ridden, for instance, a single-cylinder motorcycle, or if you felt the vibration coming from a single-cylinder engine on a lawnmower, you can see that these inertial forces can create quite a bit of vibration. There's a modification to the slider crank that's called the offset slider crank. We can see that here in this picture. The offset slider crank has the center of rotation, up here where my pointer is, offset from the path of the piston. You can see that we are generating a stroke in this design, and that we also have the conrod called out as a length L and the crank called out as a length R. We are also showing some angles defined here. The angle beta is between the end of the crank, where my pointer is now, and the end of the crank, where my pointer is here, when the piston is either at its most retracted position or most extended position. The angle alpha is the supplement of beta. So alpha plus beta are equal to 360. Another thing that we want to look at is the parameter E. E gives us the offset between the center of rotation and the path of the piston. For this kind of mechanism to work, it's necessary that E is significantly smaller than the length of the conrod minus the length of the crank. This kind of mechanism also has a very interesting property in that its forward and return strokes take a different amount of time. We can determine this pretty easily by looking just at this picture and seeing that if the crank, R, is rotating at a constant angular velocity, it will have to rotate a shorter amount of time to cover the angle beta than it will the angle alpha. This is called the ratio of forward to return stroke time, and it's equal to the angle alpha divided by the angle beta. Just by geometry, we can calculate everything that we need in order to determine that forward to return stroke time. The angle phi1, shown right here where my pointer is, can be seen as the inverse sine of the offset E divided by the length of the conrod minus the length of the crank. Theta 2, where my pointer is now, can also be found with a similar simple equation. That allows us then to calculate alpha and beta and find that offset slider ratio. The stroke can also be calculated just geometrically. This is fairly simple trigonometry. So take a few moments now, if you would, pause it, and try and convince yourself that the stroke can be found with this equation. Alright, I'm sure you all just paused it. That was great. Why don't you take the opportunity now to get out your calculators, and using these parameters, r equals 11, l equals 29, and e equals 14, go ahead and calculate phi sub 1, 2, alpha, beta, and the stroke, just to get used to it. Alright, that offset slider crank is one of a family of mechanisms that are commonly called quick return mechanisms. They're pretty interesting mechanisms in general. These are oscillating or reciprocating mechanisms, and they have an intentional difference between the time required for one stroke versus the other. These three mechanisms, crank rocker, the slider crank if it's offset, and the drag link, all function as quick return mechanisms. And these have been used for a variety of things over time. There's a sample problem, sample 1.7 on page 45. As I think I discussed in the first lecture, we won't be going over every sample problem, but I will highlight ones that we are not going over. You should take the opportunity outside of class, take a look at this. Most of the sample problems are very, very helpful for doing the homework, and hence very, very helpful for studying for exams. Alright, continuing on. Section 1.10 discusses linkage interference. Linkage interference is an interesting topic. If you will recall from the mechanism that I brought to Lecture 1, interference occurs when things bind up. Because of this, let's go back to this, all these planar mechanisms are not truly planar. All the linkages don't exist in a single plane. They actually exist in a series of parallel planes, which then are fastened together by joints. When we have linkage interference, that's often a design problem, unless you're designing it in place for linkage interference. A little later in the course, I will be bringing in a piece that has a specific interference. It's used as a hinge, and that interference is meant to act as a stop to the hinge motion. Okay, mechanisms for specific applications. I know we're going over this fairly quickly, but you'll probably appreciate that. There are lots of sources for different mechanisms. Mechanical engineering, as we've discussed, is a fairly old technology, and as such, a lot of different things have been tried and learned. If you're interested, there are a number of books that I've thrown the cover up here that you can go and reference for various mechanisms. I would also strongly recommend, if you have the chance, go and visit Henry Ford Museum. It's a wonderful place for a mechanical engineer, and if you go into the back section where all of the old engines are, you'll see some tremendously intricate mechanisms for performing a whole series of different kinds of motions. We'll look at a couple of those pictures momentarily on the screen now. So let's see here. These are kind of fun. They show some of the variety of mechanisms that we will see at various times in mechanical engineering process. This is a video of an Atkinson cycle engine. This is a style of internal combustion engine. It was generated initially to get around patents that Otto had on the standard engine that we're more familiar with. The interesting thing about the Atkinson cycle is that in some ways it's a little bit more efficient than the Otto. So if you look at many of the hybrids that are currently on the road, you'll find that their Otto cycle engines have been modified so they actually make use of the Atkinson cycle. They unfortunately don't have this really cool mechanism though. This is an old style of steam engine that's called a grasshopper beam. One of the problems in mechanical engineering when we were looking at developing these kinds of engines long ago is trying to generate a straight line motion so that we can use something like a crank slider or a piston slider. This was one mechanism to do it, and it's named a grasshopper because it does resemble a grasshopper's legs. Here's the standard Otto cycle engine. Nothing too surprising here. It is a 4-stroke engine, meaning that it brings in a charge of fuel, compresses it, ignites it, and then exhausts the remains in 4 strokes. So this is pretty much a standard internal combustion engine for almost every automobile out there. This is an interesting one. We use the Otto cycle and the Rankine cycle most commonly for our heat engines. The Otto cycle for internal combustion and the Rankine cycle for things like steam turbines. But that is not the only kind of thermodynamic cycle that can be used as an engine. This particular design is called a Ross-Stirling engine. It makes use of the Ross cycle, the Stirling cycle, which, at least theoretically, is one of the most efficient thermodynamic cycles out there. In practice, though, it's not terribly powerful, and it's not fully reversible, so many of the efficiency gains that are at least theoretically possible aren't realized. But this is a very interesting linkage to implement a Stirling cycle. We may be looking at this later on as a potential for things like course projects or for extra credit problems. So you might want to look it up. It's kind of fun. Okay. Everyone always likes the Wankel rotary engine. This is actually an implementation of the Otto cycle, but with very, very different hardware. This was developed and actually managed to bankrupt a company in Europe, the company that developed it. The only company that has effectively marketed Wankel rotary engines is Mazda. But Wankels have a couple of problems. If you note the tips of this interesting looking triangle, that is where the seals must be effective for a Wankel engine to work properly. And that's a very difficult technical challenge. Also, this engine is not terribly efficient. It's very smooth, very powerful for its size, but the combustion tends not to be complete, so it has emissions difficulties. Mazda, as I understand it, is looking at bringing the Wankel back onto the market. It's been off for a while, but we'll see how effective it will be. One more to look at. This is the Watt steam engine. So one of the probably more historically biased engines out there. It has a very interesting mechanism, again, for trying to generate a straight line. And if you're curious, it's worthwhile looking up some of the history of trying to generate a straight line with mechanisms. I'm kind of geeky that way. All right. So now to wrap up the lecture for tonight, putting things together a little bit, we've discussed in the first lecture, and then just a little bit in this one, degrees of freedom. In the first lecture, we discussed Grubler's criterion and 4-bar links, Grashof mechanisms. We also talked about one of the common limitations of mechanisms being the transmission angle, and that we need to maintain the transmission angle between suitable values, or a mechanism will have a tendency to bind up. Finally, we talked a little bit about limiting positions. Limiting positions tend to be very important in our mechanism design because we really would like our mechanism to do what we want it to do. All of these things are among the features that you need to consider as you design any mechanism. Not least of which you're going to have to think about things like materials I can make it from, how tight the tolerances need to be for my mechanism to function, what is the cost of my mechanism, what kind of performance do I need from it. These are all things that we need to do trade-offs on in order to come up with an effective and reasonable design. As per normal, with all of these lectures, I try to give you a number of references so that you can be just as excited about all of this stuff as I am. Tonight we've got some references for the K-Model library at Cornell. These are a whole series of physical models that were constructed around actually the United States and worldwide in order to help teach mechanisms to students like yourselves. As computers have gotten better, we've moved away from having lots of physical models available. I will bring in models from time to time because I think they're helpful, but we don't have models for every mechanism. Still, Cornell has a really interesting collection. You can go through it, Many of them have videos. Really kind of fascinating to review. There's some interesting things regarding reciprocating mechanisms, cam springs, a little bit on quick return designs, and then the Whitworth linkage. The Whitworth linkage is a very interesting quick return mechanism, and it was actually used as a machining technique at one time. So, if I remember at the beginning of next lecture, we will take a look at the Whitworth mechanism. That's all for tonight. Please do take the opportunity to go through the book, and I will see you at our next in-person lecture. Thank you very much.